Hi, I'm Yun-Sheng from National Tsinghua University, Taiwan. I'm going to introduce our work, OPTR, Order Preserving Translation and Recovery Design for SSDs with a Standard Block Device Interface. This is a joint work with my advisor, Professor Ren-Shuo at National Tsinghua University. As a drop-in replacement for hard disk drive, solid-state drive inherit the interface and a weak guarantee from hard disk drive. That is, they permit persisting write requests in an arbitrary order. The implication of having the weak guarantee is that for applications built on SSDs, such as file systems and database systems, they need to frequently flush SSDs to ensure order at the cost of performance degradation. We propose order-preserving SSDs, which provide two additional request level guarantees. First, they persist all write requests in order. Second, they persist each write request atomically. Our design of order-preserving SSD uses the identical interface to existing software and offers comparable performance to traditional SSDs. Let me first illustrate the difference between traditional SSD and order-preserving SSDs with an example. In this example, the SSD receives 3 write requests before a crash occurs. Here's a few valid post-crash states for traditional SSDs. For instance, write 2 can be done even though write 1 is not, or write 1 can be partially done, and many other possibilities exist. Because each sector can be either written or not, the number of valid post-crash states is 2 to the power 6. In contrast, order-preserving SSD only allow 4 valid post-crash states. We can see from this example that order-preserving SSD significantly reduce the number of post-crash states that applications have to handle. This is an apparent advantage of order-preserving SSD against traditional SSDs. The impact of order-preserving SSD on computer systems are several-fold. First, order-preserving SSD can allow us to optimize existing applications by removing unnecessary flushes. But we believe that it is practical and manageable because order-preserving SSD keep the interface intact. Second, order-preserving SSD can inspire new file system, database system design, which exploit the strong crash guarantees. Third, order-preserving SSD may establish new SSD industrial standard. Finally, order-preserving SSD itself can open a new research direction in the area of SSD firmware. So I've covered what is an order-preserving SSD and its implication to system design. Next, I will briefly describe some background knowledge regarding SSD and their recovery, and introduce our SSD design which preserves order while maintains high performance. Then I will demonstrate one usage case of order-preserving SSDs, which is to optimize existing applications. Finally, I will conclude this talk. One main constraint of flash memory is that it does not allow in-place update. Thus, most SSDs are embedded with a specialized firmware called Flash Translation Layer, or FTL for short, for logical to physical address mapping. To achieve high performance, SSDs often consist of multiple channels and flash chips to increase the level of parallelism. Besides, FTL may reorder requests and employ a write cache to improve response time and throughput. Although these high-performance schemes are very useful, they also inevitably break the order. FTL are also responsible for garbage collection and crash recovery, which I will cover in the next slide. Pages not containing the most recent data, which we call invalid pages, will accumulate in flash memory. Thus, garbage collection is required to reclaim space for future write. During GC, a victim block is chosen and each valid page in the victim block is copied to another page. Then, FTL updates the L2P table to relocate the copied page. Finally, the victim block is erased. Crash recovery is another task FTL has to handle. Since the mapping table is often kept in volatile memory, FTL has to reconstruct the L2P table after a crash. This is normally done by leaving an LPN tag in the spare area of each programmed page. So during recovery, FTL can examine the LPN tag and reconstruct the mapping table. Okay, so that's enough for the background knowledge. Let's get down to our design. As mentioned earlier, we want our design to preserve order while maintaining high performance. So we need to keep all the high performance schemes. This means that write requests are not necessarily processed in order. However, the recovery procedure should be able to roll back the SSD to a desired state, which creates an order-preserving illusion. For clarity, let's first assume an SSD without a write cache and GC. We'll remove this impractical assumption in a minute. The key idea of order-preserving recovery is that during recovery, if we know exactly which writes are complete and which are not, we can recover until the first incomplete write. For example, if the first, second, third, and fifth writes are complete, then we can simply recover the first 3 writes, but not any other write. The follow-up question is, how can we determine whether a write is complete or not? We introduce a mechanism called write completion tracking. The key idea is really simple. If a write contains n pages, then, and during recovery we find n pages for the write, then the page is indeed complete. Otherwise, the write is incomplete. So we leave 2 tags in the spare area of each page, write ID and size. Write ID is a sequence number assigned to a write, according to the order in which writes are received by the SSD. And size is the number of pages the write contains. By doing so, determining whether a write is complete is simply a counting problem. If the number of pages found for a particular write matches the size tag, then we can conclude that this write is complete. Otherwise, the write is incomplete. Let's try to recover an SSD with 8 pages programmed. Each page in the figure is represented by its write ID, size, and LPN. The first step of our recovery procedure is to read out all the program pages and reuse the information we left in the spare area to determine whether each write is complete or not. Next, we can construct a flow network with each node representing a write request and each edge pointing from write I to write I+1. Then we find an SD code to partition the network into 2 subgraphs, S and T, such that every write in S is complete and the size of S is maximized. Finally, we can recover all the writes and only the writes in subgraph S. So that's basically the idea of order-preserving recovery. Next, I will remove the assumption that I made previously, that is, no write cache and GC. One of the benefits of a write cache is write coalescing. We want to support write coalescing because when 2 write coalesce, the number of program operations required decrease, and therefore the performance and lifetime of an SSD increase. However, the recovery procedure shown previously is incompatible with write coalescing. Let's take a look at an example. In this example, write 10 contains 2 pages, and both pages are buffered in the write cache. While the first page has been written to flash memory, the second page has not. If another write, say write 11, targets the same pages, then the first page is replaced, which is fine. But the second page is coalesced, and the consequence is that write 10 will never be considered complete because its number of pages that can be found during recovery is at most 1, while the recovery procedure still expects to see 2 pages in order to consider write 10 as a complete write. From the above example, we can see that the main challenge is that write coalescing decreases the number of pages being programmed to flash memory, and therefore the number of pages found during recovery can no longer match the number of pages the write contains. A naive solution would be forbidding write coalescing. However, write coalescing has its benefit, and we don't really want to do that. What we really should do is to have knowledge that coalescing happens. So we introduce coalescing records to keep track of coalescing events. Coalescing records serve 2 purposes. First, it tells the recovery procedure to expect 1 less page for each record. Second, write requests that coalesce are atomic as a whole. Consider the previous example. This time we augment each buffer a write ID and a size. When a coalescing event occurs, which can be detected by the dirty flag, we form a coalescing record consisting of the write IDs of both write and the size of the prior write. Coalescing records are recorded in a buffer, and a batch of coalescing records are written to flash when the buffer is full or upon receiving a flash request. Garbage collection is still incompatible with our recovery procedure. The reason is that the job of a garbage collector is to reclaim invalid pages. However, our recovery procedure relies on these invalid pages to determine whether each write is complete. To resolve this issue, we perform mapping table checkpoint. We conduct two types of checkpoint: incremental checkpoint, which record only the mapping table difference compared to the latest checkpoint, and full checkpoint, which record the entire mapping table. We always perform incremental checkpoint except when we're out of storage. Once the checkpoint is successfully created, all write requests prior to the checkpoint is guaranteed recoverable, and thus, these write requests do not rely on the counting mechanism to determine whether they are complete. This solves the GC issue because now we can restrict GC to only reclaim pages programmed before the latest checkpoint, but not those after the latest checkpoint. Let me show you the final recovery procedure that is compatible with write cache and GC. Description colored in purple are those that differ from the previous recovery procedure. The recovery procedure starts with sequentially applying all checkpoints. Then it reads out pages and coalescing records generated after the latest checkpoint. Next, the recovery procedure determines whether each write is complete or non-incomplete. Incomplete writes are those that have total number of pages and coalescing records fewer than the number of expected pages. The recovery procedure then constructs the same flow network as the previous one and add a band age for each coalescing record. In addition, for the previous constraint, we add another constraint. The cut size has to be equal to 1. This constraint captures the idea of coalescing writes are atomic as a whole. Finally, like the previous recovery procedure, we recover all the writes and only the writes in subgraph S. Okay, so let me explain our evaluation method. We implement order-preserving SSD on a hardware platform and validate it against our previously proposed testing framework called the VST. We modify the Ext4 file system and the SQLite database system to exploit order-preserving SSDs. We identify 3 system optimizations with order-preserving SSDs. The first one optimizes the file system. The second one optimizes both the file system and application. The third optimization is a no-flush mode enabled by our proposed order-preserving SSDs. These slides explain the baseline before we dive into the 3 system optimizations. We run SQLite on top of Ext4 on top of a traditional SSD. For the figure on the right-hand side, the x-axis denotes the changes we made to the system, and the y-axis denotes the performance of the system. The green point denotes the baseline. Previous work on transactional SSDs proposed to change, or in some sense, to abandon, the standard disk interface so as to achieve the desired strong crash guarantee. Although they can potentially achieve substantial benefits, they also suffer from significant system changes. In the first system optimization with order-preserving SSDs, we optimize Ext4 by allowing a redundant flush request of fdata sync to be removed. Experimental results show that we can obtain a 1.3 times speedup. In the second system optimization, we further optimize SQLite by replacing some fdata sync with a new file system API called fdata-fence. fdata-fence does not use flush at all and relies on our SSDs to implicitly preserve the order. By doing so, we can achieve a 2.8 times speedup. In the third system optimization, we keep both Ext4 and SQLite intact, but mount Ext4 using the no barrier option, which suppresses all flush requests. This mode traces away immediate durability for achieving a 6.2 times speedup. Please note that even if this mode suppresses all flushes, crash consistency is not traded away because our SSD can implicitly preserve the order of write request. In conclusion, we propose order-preserving SSDs, which provide 2 additional request level guarantees. First, they persist all write requests in order. Second, they persist each write request atomically. We believe that order-preserving SSD should be an interesting topic and may have several impacts to computer systems, including optimizing existing applications, inspiring new file system and database system design, establishing new SSD industrial standard, and opening up a new SSD research area. That's all for this talk. Since I'm still refactoring the code and writing document for it, the code is currently not available, but we will make it available before August 15. Thank you.
Questions? Yeah, I have a question. You mentioned that on recovery you have to read out all of the pages to get the write IDs and so forth, that information. What is the cost of doing that readout? I mean, there's a lot of pages on an SSD.
Yeah, so actually, only the naive algorithm read out all the program pages. So since we have done checkpoint, we only need to read the pages programmed after the checkpoint. So we do not need to read all the program pages in the entire SSD.
And so how long does it actually take in practice?
We did not evaluate the recovery time because the hardware platform we implement the algorithm has some hardware limitation. So we implement the recovery algorithm on a simulation framework. So I'm sorry that I can. So we have done some analysis based on some worst case assumption that should take maybe three seconds less to recover an SSD.
Also, I was curious, your graph algorithm where you find the cuts in the one that has the bent edges as well as the straight edges, is it always possible to find a cut that has just one edge?
Yes. Once a flush request is successfully performed, there will always be a one cut. One cut. Yeah.
Any other questions? Okay. Well, I would like to thank everyone for coming. It's been a great conference. I hope you guys have enjoyed it as much as I have. And I wish you all safe travels on the way home. Thank you for coming.